So ratios, unit ratios, rates, these are all subtly different ideas, and in this video we're going to try and tease out the differences between them and how to work with them so that we can answer, for example, exam questions. So let's just start with what we know about ratios. If we've got 5 letter boxes and we've got 30 letters, then we can say, well, the ratio of letters to letter boxes is 30 to 5. And the first idea that I want you to think about is unit ratios. So a unit ratio is a bit like a fraction. A unit fraction would be if we had 5 out of 30, and we would simplify that down to 1 out of 6. And when it's got a 1 on the top, we call that a unit fraction. Well, here, to get a unit ratio, we sort of want 1 on the bottom. In other words, we want this to become 1. Okay, so if that's to become 1, then we have to divide by 5, obviously. So 5 divided by 5 gives us our 1. Here, then, because they're directly proportional, we also divide by 5, and 30 divided by 5 is 6. Now, no news there. You can see, in fact, if I remove 4 of these letterboxes, you can see that we've got 6 letters per letterbox. However, this is the fundamental concept that we need to be working with when we're talking about rates and compound measures. So let's just have a look on the graph. 30 letters then, 5 letterboxes we could record here. 6 letters, 1 mailbox, and we can record that there. We can see that they're directly proportional just by thinking about it, and by drawing a line down between the 2 points, we can see that if we had no letterboxes, continue that line, we would have no letters, so 0, 0. So that's the basic idea here, and we end up with something that we generally call 6 per letterbox, so 6 letters per letterbox. So in fact we might write this slightly differently to how we normally write a ratio. We might write it with a forward slash, for example, just to distinguish it from the usual ratios that we're working for. And the key idea is here is per, so we've got 6 of something per 1 per unit. Okay, let's now think about if we introduce some measures. So instead of having objects now on both axes, if you like, of our ratio diagram, let's now think about having something that we can measure. So in this case, what I'm going to do is have pounds. So if we think of a money example, and let's get rid of these now. And so if I've got 2 dozen oranges, there we go. So if I've got 2 dozen oranges, how many oranges have I got? I've got 24. 24 oranges, let's say, cost me £6. What I naturally want to find out if I'm going to buy these oranges is how much does 1 orange cost me then? How much does 1 orange cost me? So on my graph here, if I've got 24 oranges at £6, I can mark that on here. I expect them to be directly proportional again, so if I go down to a unit rate, then I'm going to be going down proportionally, so both sides I'm going to divide by the same amount, and the amount I'm going to divide by is found on the right hand side then of this ratio. So divide by 6 and I'll get my unit rate. Okay, if I divide this side by 6, 24 divided by 6 is 4. So I've got 4 oranges now for £1. In fact, I might as well put my pound sign in here now. So let's put those 2 values on here so that we can see that. We've got our 24 here. Now we go down to 4 for £1. So 4 oranges. So I've got 24, I've now got 4 oranges, which is down here, and £1, which is about there. So 4 to 1. So again, if I drew a line down to 0, you can see visually the directly proportional relationship. And I could calculate up, obviously. With both these examples, I could go up to find out how many 100 oranges would cost. And it's very easy when you've got the unit ratio. Now, we haven't got what we call a unit price yet. So what's a unit price? Unit price is a slightly different concept. If we think about price as our unit, then we want this side of our ratio to be the unit. So we want this side to be 1. Okay? So what have we had to do to get that 4 to be 1? We've had to divide by that 4. And therefore we now have 1 orange costing us what? £1 divided by 4, 25p. Okay, so the unit price or unit cost is 25p. And once we've got that figure, we can sort of think, well, is an orange worth 25p? Do I want to be paying 25p per orange? And this gives us very much the idea of a rate. A rate is really when you've got not just a unit on one of these axes, so here we have pounds and pence, but you've got units on both axes, so you're comparing two measures. Let's have a look at an example of that. Well, the most obvious and perhaps the first example to come to mind will be speed. So let's think of an athlete now, okay, who's speeding along. And I'm going to think of a couple of other ratios as well, but let's just start with speed. So speed is very much a rate. You know, we say what rate is somebody travelling? What rate is something moving at? And we can calculate his rate. Let's say he's travelling at 30 miles. So he's covering a distance of 30 miles. So these will be miles. In 5 hours. So this will be time t, so a t-axis and a d-axis now, and this will be 5 hours. So our unit is going to be 1 hour. So if he travels, let's call this problem A, if he travels 30 miles in, let's write it in full here, so 30 miles in 5 hours, then how far has he travelled in 1 hour? So in other words, what's the unit rate here? Well, again, if we divide both sides by 5, so both sides by 5, then we will get the number of miles per hour. Okay, so per 1 hour, or just per hour. 30 divided by 5 is 6, so we get 6 miles per hour. Or we might want to write that simply as 6 miles per hour, which is how we usually write miles per hour. Okay, so what it means, a rate is 6 of one unit per 1 of another. So in this case, 6 miles per 1 hour. So we've got 6 miles per hour. Now the other way that ratios come in here is if we're converting. So let's say we want to convert miles per hour to meters per second. Okay. Now what's the unit conversion for miles to meters? Well, we need to know the conversion rate, or conversion ratio, for miles to meters, or meters to miles. So for every 3 miles, let's say, for every 3 miles, how many meters? Well, that happens to be 4,828. 4,828, thereabouts, meters. So we've got a 3 to 4,828 ratio. Now, a good idea here when we're converting something like this is to think, well, do I want to scale up this number or do I want to scale it down? And I want to scale it up. I want to have meters now per hour, and then I'm going to have meters per second. But I'm going to start with meters per hour. So if I take this figure here, 4,828, 4,828, multiply by my 6, but also have to divide by my 3 so that I get my unit rate. So 4,828 divided by 3 will give me my unit rate, which is about 1,609 to 1. But I don't have to make that conversion at the moment. I've got it in this fraction here. So all I need to do now is calculate the answer here, and I've got 6 divided by 3, so I can do some cancelling here and get 1, 2. Multiply across, and I get 2 times 8, 16. Carry the 1. 2 times 2, 4. Add the 1, gives me 5. 2 times the 8, 16 again. Carry the 1. And 2 times 4 gives me 8 plus 1, 9. So I've got 9,656 meters per hour. To get meters per second, I need to do another step. Okay, so if we call this step 1, now let's do step 2. So how do I get per second? Well, I've got hours. It's safer perhaps if I go down to minutes. So that would be 9,656 going down to minutes. Then I'm going to divide by how many minutes there are in the hour. Okay, obviously in 1 minute he's going to go a much shorter distance. I want to divide, so it's dividing by 60. If I then want seconds, I divide by another 60, because he's not going to go very far in a second. And so there I've got my my answer, once I calculate it out, of how many meters per second. Meters per second you'll sometimes see written like that, or we can just use the convention we've been using, which is a / here. So 9,656 divided by 60 and divided by another 60, or you could say 9,656 divided by 3,600. So 9,000, if I use my calculator, 9,656 divided by 60 divided by another 60 gives me 2.68 and 2 recurring. 2.68, 2 recurring then, meters per second. And if I simplify that, let's say it asks me to 3 significant figures, then I'll say he's travelling at 2.68 meters per second to 3 significant figures. 3 significant figures there. Okay, so that's the sort of calculation. It gets rather more complicated as we work through these conversion problems, but basically nothing's too difficult to understand. It's a pretty sensible kind of thing that you just have to go through it step by step, steadily aiming towards the answer and checking all the time for reasonableness. Is the answer I've just given reasonable? Is it reasonable that he travels 2.68 meters per second? Yes, I think it is. Sounds about right. So I'm going to say that that is correct. Okay, let's try another one. This time what we're going to do is look at density. So if this was speed, which is distance over time, so speed is distance over time. Let's look now at density. Not density, pressure. So let's do this one here, pressure. Now pressure, which is measured in pascals usually, pressure is the force downwards. So force is in newtons, so force divided by the surface area of the foot in this case here. So how much area is in contact with the ground in this case. So we're going to measure that in cubic centimeters or cubic meters. And so what we'll say is force divided by area, where A stands for area. Okay, so pressure is force divided by area. Okay, let's think of a problem then, some numbers then that we can work with. So let's call this problem B. And let's have 75 newtons for every 5 cubic centimeters. So keep the numbers fairly simple to start with. So here we've got area, 5 cubic centimeters, and here we've got force, 75 newtons. So on our axis now, we're going to have force in newtons, and on our x-axis, we're going to have area in, well, actually what we want ultimately is meters squared, but let's have at the moment centimeters squared. And we didn't actually mark on our speed here, so we started with what, 30 in 5, so let's mark that on here, 30 in 5. Now we're starting with 75 newtons here, so it's going to be about there, 75 per 5, so 75 5, which is about, yeah, it's going to be halfway, isn't it? So it's going to be there. Okay. So again, what we're trying to do is just as we did here, where we tried to bring, we didn't just try, we brought it down to 6 here. We need to bring this one down, scale it down again to get our unit. Okay, so again, right down here. So the graph is an interesting way of looking at it. I guess you wouldn't normally do it in this way, but we're looking at, well, about there, aren't we? Okay, so just a little sort of extra check by using the graph to see what's going on. Okay, but just numerically, very easy to do. This side we've got to divide by 5 rather, and this side then also by 5. So we've got 75 divided by 5 equals, equals 15 newtons per square centimetre, not cubic centimetre, square centimetre. So divided by area. So 15 newtons per square centimetre. Sometimes you'll see it like that, but usually we just use a forward slash like that. Okay, so 15 newtons per square centimetre. Now what if we wanted newtons per metre squared, which is pascals? Well, let's think about how many square centimetres there are in a square metre. If I draw just very roughly to one side here, a kind of area here, then I would have for a square metre, if this is 1 metre, 1 square metre, then along here I must have 100 centimetres, and along this side too I've got 100 centimetres. So for a square metre I must have 100 times 100, in other words 10,000. So there are 10,000 square centimetres in a square metre. Do I then multiply this figure by 10,000? Well, no, because the area is dividing into the force. And if I think about it, it makes sense. Spread over this much larger area now, the force is going to be much less. So I want to divide by 10,000. So my conversion rate to get me from square meters to square centimeters to square meters is going to be divided by 1,000. So it's going to be 1 square meter to every 10,000 square centimeters. So just jot down your conversion rate there so that you don't make any mistakes. Okay, so now we're going to divide then this 15 by 1,000, giving us 0.0. Have I got that right? Yeah, 15. And just to check that you do have that right, you've got to move the decimal places, the decimal point 4 places. If you move it 4 places to the right, 2, 3, 4, you end up at 15. So it's a good idea just to do that check to make sure you haven't put in an extra 0 in, and you've got that correct. Okay, so we've now got 0.0015 newtons per square metre, which we can rewrite as pascals. Okay, or 1.5 times 10 to the minus 3 if you prefer standard form. Right, finally, let's have a look at density. So let's just give ourselves plenty of room. So let's now work on a density example. Now density is mass over volume. So if I think about my axes now, I'm going to have, let's just put that back, I don't know why that went. We've got mass as the dependent variable, measured in kilograms or grams, and we've got volume measured in cubic centimeters or liters. So we'll start with liters. That's kind of capacity really, but it gives us a starting point for this problem. Let's give ourselves plenty of room. Start over here. Okay, so what I'm going to do now is think about something like 12 kilograms. Let's say we knew that we had, for 12 kilograms of bone, 7 litres. So that would be how we would get our density. Density, remember, is measured in kilograms per, well, usually kilograms per square metre or grams per square centimetre. So let's convert to grams per square centimetre. But we're starting in litres. So we've got kilograms per 7 litres. Let's now get our unit conversion then. So a unit rate rather. So what we want is just 1 litre. So we're going to bring that down to 1 litre. So if I divide by 7, I have to do the same here. Divide by 7 and I'll get 12 over 7, which is 1 5/7, which gives me 1.7. I'm just going to work to 2 decimal places, so 1.71 kilograms then for every litre, so kilograms per litre. So that's my unit rate, 1.71 kilograms per litre. Now my conversion, and this is where people often get confused, if I have 1 cubic meter, what's that going to be in litres? Well, 1,000 litres will give me a cubic meter. Okay, so I can rewrite this now. 1.71 kilograms to every well, it's got to be 1 divided by 1,000 then, hasn't it? So 0.001 cubic meters. So that's done that bit of the conversion. Now the bit that I find that people always find tricky is this one, is when they have to convert cubic meters to centimeters. How many cubic centimeters are there in a cubic meter? Let's again go to one side, draw ourselves a little diagram and think about this. If this was a cubic meter, so a cubic meter, how big would the sides have to be? Well, each of the sides is 100 square centimeters, so we've got 100 along this side, so 100 centimeters in a meter, 100 centimeters along this side, and the height must also be 100. So it's 100 times 100 times 100, and that's 1,000,000. So I think one of the commonest mistakes is not realizing this conversion. It may be given to you, but it's well worth remembering. So 1,000,000 cubic centimeters, so a lot, in a cubic meter. Okay? Well, now we can convert then our 0.01 meters cubed to what? We've got to multiply by 1,000,000. So we move our decimal place, in other words, 6 places to the right, our decimal point 6 places to the right. We'll end up with, I'm just going to use the eraser, we'll end up with 1,000. Okay, cubic centimeters. And if you weren't sure about that, then always just do that check and move the decimal point again 6 places to the left, and you should find you have that 0.001 cubic meters. Okay, now we're nearly there, but we've got to convert our 1.71 kilograms to grams. Well, that is a nice and easy one. 1 kilogram equals 1,000 grams. Okay, so we've now got 1,710 grams per 1,000 cubic centimeters. And so, if we divide both sides by 1,000, we get our unit rate, which is 1.71 grams per cubic centimeter. And there we go. And does that sound reasonable? Well, what I've noticed is that we've ended up with the same as we had up here, 1.71 kilograms per litre. Now we've got 1.71 grams per cubic centimetre. So I can use my graph here again. I had 12 to 7, but then when I found my unit rate, I had 1.7, should be about here, nearly 2 then, to 1, and if I join that up again, I should get a straight line. So I'm going to say that that answer there seems to be correct. So let's just compare, or just summarize what we've been looking at here. So we had speed, which is distance over time. We had pressure, which is force divided by area. And we had density, which is mass over volume. And these three things, I think, are the main rates that you're going to come across. So this is basically a rate, speed is a rate, pressure is a rate, and density is a rate. And so what do we mean exactly by rate? Why do we have this term rate? Well, generally we think of it as how fast something happens. So a rate is, especially when it's a speed, is how fast something happens. Lots of things in real life tend to get expressed by time. So I guess that's why we think of it as how fast. Rate of pay, for example, or rate of growth are both examples, again, that are time-based. So a rate we tend to think of in terms of time. By formal definition, rate, in fact, is a comparison of two terms in a ratio when the two terms are in different units of measurement. So you can see here the units of measurement, obviously here, are meters and let's say seconds. So that adds to our definition of a rate. Speed, the rate of speed, is distance per time, distance over time, measured in this case, meters per second. Here we've also got a rate, but this time we've got force is measured in newtons, so this is newtons, and area is in centimeters squared. Here we've got grams or kilograms, and here we've got centimeter cubed. But you've always got this common thing of a comparison of two terms in a ratio, in this case in a directly proportional ratio, in all three cases, so all three are directly proportional. So if you increase one, you increase the other, and vice versa, directly proportional relationship. But also you've got this idea of them being actually measures in both terms. So you have a measure in both the first term and the second term in the ratio, and because they're measures, they're in different units of measurement. Now I've just drawn up this formula triangle because you'll often come across this, and it's a very useful technique for rearranging these formulae. So if you have distance, speed here, and time, you can get in fact three formulas for the price of one in this triangle. So you have speed is distance divided by time. If you look to the distance and cover that up as it were, then what you're doing is fixing the distance and looking at speed and time. So then you will have distance equals speed times time, which if you rearrange this algebraically, you will get distance is speed times time. You can also cover up the time segment here, and you've got time is distance divided by speed. And so that's a really useful little tool as well. You can do the same for pressure. So if we erase these now, let's use a different colour. Okay, so for pressure, we've got force divided by area. So pressure is force divided by area. Well, we can equally say that area is force divided by pressure, or force is pressure times area. So you don't have to remember three formulae, you just remember one, or you remember this triangle, fit it into the triangle in the correct way, and you can get three for the price of one. Let's have another go. Finally, let's have a look at density then. So for density, how do we fill in the triangle? Okay, so density goes down here, and we've got mass divided by volume. So we can say density equals mass divided by volume. But equally, cover up the mass and we get mass is density times volume. Or we get volume is mass divided by density. So hopefully the formula triangle is a useful device for you to use. Don't forget though to make sure you understand how it works. And you don't necessarily need it, because if you know how to algebraically rearrange equations, in other words, here what we did was we multiplied both sides by v, and that gave us mass equals d times v, and then from here we divided both sides by d, giving us v equals m divided by d. So you can do it algebraically, and you should certainly be practiced in doing that, but I think these triangles are quite a useful way of just making life a little easier. Fill in the triangle correctly and you have 3 formulae for the price of 1.